with the lessons. And in the last class, we were talking about the alkaline fuel cell. And this alkaline fuel cell is a classification based on the type of electrolyte, and as the name itself indicates, the electrolyte is an alkaline solution. Advantages: so high current density, so lower cost, so non-noble electrodes made of non-noble metals, and there is no bipolar plate, and activation losses are low. These are some of the excuse me, some of the advantages of alkaline fuel cell. And we also learnt about the reactions working principle. So little background, advantages, types of electrodes, how these are fabricated, and disadvantages. Coming to the disadvantages, so the fuel should be pure. It should not contain carbon dioxide. If carbon dioxide is present in the fuel that enters the alkaline fuel cell, it will react with the electrolyte, that is NaOH or KOH, forming carbonates. So because of this, the availability of the OH minus ions decreases, viscosity increases, flowability decreases, and this carbonates tend to precipitate. And these are some of the reasons why it is a disadvantage. So that is all about AFC. So today we shall start with the next fuel cell, that is the phosphoric acid fuel cell. So again, the classification is based on the type of electrolyte that is used, and here in this case the electrolyte used is phosphoric acid, an acid electrolyte. So what was the conventional electrolyte that people started with? That is sulfuric acid. Comparatively, there are many advantages of using phosphoric acid, and we are going to learn that soon. So coming to the operating temperature, the range is 373 to 493 Kelvin, and it is considered as medium temperature fuel cell. If you want to classify that based on the operating temperature, then the current density is moderate. So if you want to compare these two parameters with alkaline fuel cell, the operating temperature was less than 100 degrees centigrade, close to room temperature. So that's why it was low temperature fuel cell. Here it is 100 to around 200, 220. Because of that reason, it's medium temperature fuel cell, and current density, it was high in alkaline fuel cell. So here it is moderate. And electrodes, here it is platinum electrodes, and in alkaline fuel cell it was nickel based electrodes, nickel or nickel oxide alloys of nickel. And charge carrier, here it is proton, so there it was OH minus or hydroxyl ion. And water management is evaporation in both the cases. Coming to the applications, so here it is electrical utility and transportation, so it's a grid power generation. So phosphoric acid is mainly used for grid power generation, but there are few examples where it was used for transportation as well. And applications in case of alkaline fuel cell, the space and military applications. So and soon we are going to learn more about advantages and disadvantages of phosphoric acid fuel cell as well. So this is overview. So you always have to start with the overview, and there may be questions where you are asked to compare or differentiate between fuel cells where an electrolyte is alkaline solution, and in other case the electrolyte is acid. So in that case, you are free to compare alkaline fuel cell with phosphoric acid fuel cell. So that is also a possibility. To continue, So it falls under medium temperature fuel cell, and these are certain general advantages of fuel cells which fall under the category of medium and high temperature fuel cells. So the open circuit voltage and theoretical maximum efficiency of a fuel cell reduces at high temperatures. So this is an observation, and open circuit voltage we know, but we haven't learned theoretical maximum efficiency yet. So we are going to learn that soon. For now, you just remember that these two parameters decrease or reduce at high temperatures. With increase in operating temperature, the open circuit voltage will come down, so is the theoretical maximum efficiency. In spite of that, there are certain advantages of operating fuel cell above 100 degrees centigrade. The reactions proceed faster, so activation over voltage or loss because of activation is less, and noble metals or noble catalysts are not necessary. However, in this phosphoric acid fuel cell, it is a medium temperature fuel cell, and still we talk about platinum. But when you consider high temperature fuel cells, which goes more than 500 degrees centigrade, in such a case, definitely noble catalysts are not necessary. And extraction of hydrogen from more readily available fuels is easy. That means we can make use of the high operating temperature. Because of that reason, you can subject the fuels to reforming or other processes. So pre-processing can happen within fuel cell, and the required hydrogen can be generated from fuels such as natural gas or hydrocarbons. Also, these medium and high temperature fuel cells are good for CHP. What is CHP? Combined heat and power. So if you remember, we have discussed this earlier. Along with the electricity that is generated because of the operation of fuel cell, there is some heat generated which is known as waste heat. That waste heat can be utilized to generate additional power. So in such a case, it is known as CHP system, or combined heat and power generation system. Okay, with those general advantages of medium and high temperature fuel cells, let's come back to phosphoric acid fuel cell. So let's look into the reactions and other salient features of this fuel cell, in particular the phosphoric acid. Okay, looking at the reactions, so it is more or less the same like a conventional hydrogen oxygen fuel cell. The fuel hydrogen is supplied at anode. Hydrogen splits into protons and electrons. So the fuel hydrogen splits into protons and electrons at anode. The electrons pass through the external circuit and reach cathode. The protons move through the electrolyte and reach cathode. At cathode, the oxidant oxygen combines with these electrons and protons, forming water. So these are the reactions that take place at the anode and cathode respectively. If you look at the overall reaction, it is the fuel hydrogen reacts with oxygen, forming water. Here the electrolyte is inorganic acid, which is concentrated phosphoric acid, that is 100% phosphoric acid. So it is not mixed with water. Usually for electrolytes, if you use any other acid other than phosphoric acid, you will end up adding some water. So without the addition of water, it is difficult to retain the acid in the form of ions. So whatever that acid is made of, it should split into ions, and ions should be freely available so that it works as an electrolyte. However, that is not the case in case of phosphoric acid. So why is that? So it has the ability to split itself into ions even in the absence of water. So it is known as self-amphoteric liquid. And of course, the ions are charge carriers here as well are protons. And coming to the electrode, so initially we mentioned that the electrode is platinum electrode. So in the very primitive phosphoric acid fuel cell, the entire electrode was made of platinum. However, later people started using substrates such as carbon black or graphite, and they deposited this catalyst material, that is platinum, on those substrates, thereby drastically bringing down the quantity of these noble metals involved in fabrication of electrodes. And electrocatalyst particles are highly dispersed and supported on carbon black. So here the general substrate is carbon black. And this phosphoric acid is also known for its thermal, chemical, electrochemical stability. So even if you heat it, even if you take the phosphoric acid to higher temperatures, so it has no issues. So thermally it is stable, chemically it is stable, also electrochemical stability is observed, and volatility is less. So when subjected to higher temperatures, the amount of evaporation is comparatively less when compared with other acids in case of phosphoric acid. And also one more advantage is this phosphoric acid is tolerant to carbon dioxide. That means if fuel contains carbon dioxide or oxides of carbon. So for now, let's just speak about carbon dioxide. Later, we shall talk about carbon monoxide in a while. So if carbon dioxide is present in the fuel, it is not an issue. Whatever disadvantage we had, that is formation of carbonates and precipitation in case of alkaline fuel cell, is not there in PAFC, that is phosphoric acid fuel cell. And usually these electrolytes, when the electrolytes are liquid, you cannot just contain it in a vessel the way we do it in the laboratory. So if you simply take a beaker, so fill that with acid and dip two electrodes in it, it becomes the most primitive fuel cell on laboratory scale. However, so commercially available fuel cells, large capacity fuel cells will definitely don't look like that. So what is the mechanism they use to contain the electrolyte, which is liquid? So usually they make use of a framework made of uh, composites. So here silicon carbide composite, a matrix made of silicon carbide is used, which is highly porous and structured. And the pores are defined and structured. Uh, Through these pores, the electrolyte is circulated. That means to contain the electrolyte, a matrix is used, which is highly porous. Are you still able to see the slides?
Yes, sir.
Okay. Just a minute. Is it in the slideshow mode or not? Hello, are you guys there?
Yes, sir.
Okay. Yeah. Uh, so I was talking about how the electrolyte is handled. So a matrix is used, which is highly porous, and the electrolyte, liquid electrolyte, is contained in it, and the movement of electrolyte inside this pores is through capillary action. And in particular, silicon carbide matrix is used in this PAFC. And the if it goes below 42 degrees centigrade, meaning the temperature should always be maintained about 42 degrees centigrade, above 42 degrees centigrade in case of PAFC. And coming to the fuels, in case of AFC, the applications are premium applications, so cost is not an issue. Of course, comparatively, because of certain reasons, AFC is considered as cheap. But if you consider the components of fuel cell, the cost is not high. But there are associated disadvantages because of the purity required for the fuel. So you will end up using pure hydrogen. That may add little to the cost. And such disadvantage is not there when it comes to phosphoric acid fuel cell. So fuels such as natural gas, LPG, light distillates are some of the fuels that are commonly used here. And usually when the fuel is something other than hydrogen, you will subject the fuel to pre-processing and hydrogen is generated. And extraction can happen either outside the fuel cell or within the fuel cell. Soon we are going to look at few certain examples. So here in this case, it can be usually in phosphoric acid fuel cell, the fuel processing is external. In other, there are certain fuel cells where the fuel processing can be clubbed or it can happen inside the fuel cell. And as I mentioned earlier, in general, acid electrolytes require water for conductivity, but that is not the case when it comes to phosphoric acid. And it is a unique acid which has the ability to ionize by itself. So, which always exists in the form of ions, which facilitate the flow of ions through the electrolyte. And as discussed about medium and high temperature fuel cells, it is possible for CHP. So, it is one of the electricity is generated. If you consider the current density or efficiency of the phosphoric acid fuel cell alone, where you do not take the CHP into account, in such a case, the current density is moderate and efficiency is low. But if you utilize this combined heat and power, if you use it as a CHP system, so this additional heat generation or additional power generation because of the waste heat will compensate for the low efficiency of the PAFC. So combination of fuel cell and heat engine can lead to unsurpassed levels of efficiency. Each machine compensates for the practical problems of the other. Now coming to the electrodes. So far we learned the reactions and we realized some of the salient features of phosphoric acid and advantages of PAFC. Now we are moving to the electrodes. So here usually these are commonly termed as gas diffusion electrodes. So why such a name? On one side you will have fuel, on the other side you have electrolyte. Electrolyte is a liquid and fuel is usually gas, and these gas should diffuse through the pores of the electrodes, so the name gas diffusion electrode. And in the most primitive phosphoric acid fuel cell, the entire electrode was fabricated using platinum. So here in this case, carbon black or graphite is used as the substrate, the base material. And coming to the fabrication, this PTFE, polytech, is utilized, and the platinum powder and the carbon powder both are considered, and you just using the binder you will just cast that into the required shape. And usually when it comes to the loading, the catalyst loading, it is expressed as grams per centimeter square. So here in this case, it is 9 milligrams of platinum per centimeter square. So that is how you express the quantity of the catalyst material that is utilized or required to fabricate the electrode. And again, it depends on the electrode. If it is anode, certain loading is used, and if it is cathode, the loading might be different. So in the beginning it was completely platinum, then they reduced the usage of platinum by using different substrates, and they brought it down to as low as 9 milligrams per centimeter square. Later it was further reduced down to zero point 0.1 and zero point 0.5 milligrams of platinum per centimeter square of anode and cathode respectively. So that is the extent to which the usage of platinum is reduced. So it will have a huge impact on cost. And irrespective of the catalyst and the fuel cell or the electrode, the catalyst activity depends on the particle size distribution and surface area that is created because of the size of the catalyst particles. And this is how the electrodes of phosphoric acid fuel cell are fabricated in general. Of course, depending upon the application and capacity required, there might be many variants within the phosphoric acid fuel cell itself. This is just an example of how you fabricate electrode in case of PAFC. Okay, so now we realized that in most of the cases in phosphoric acid fuel cell, the fuel is not pure hydrogen. So we always start with material which involves pre-processing of fuel, so such as natural gas, LPG, or hydrocarbons. So one of the ways of pre-processing or obtaining the required hydrogen from fuels such as hydrocarbons is steam reforming. So the same method is used in the PAFC as well. And what you do here is you subject or allow the hydrocarbons to react with steam, and hydrogen and carbon monoxide is generated because of that. So let's take an example of the simplest hydrocarbon, that is methane. So methane reacts with steam, which is nothing but water. So generating hydrogen and carbon monoxide. And usually this steam reforming is not just one reaction. There is one more side reaction that takes place. So this carbon monoxide again reacts with steam, forming carbon dioxide. So these two reactions often take place simultaneously. And we are going to learn more about this steam reforming in Unit 5. So now if you want to generalize this reaction to any hydrocarbon, So we started with methane and you want to generalize it to other hydrocarbons. So this is how it is done. So CXHY reacting with X molecules of steam or water. So generating certain quantity of hydrogen and carbon monoxide. And usually the steam reforming reaction is endothermic. You will end up supplying external heat. So this is the reason why the fuel processing can be clubbed with a fuel cell which operates at a temperature greater than 100 degrees centigrade. So because of that high operation temperature, a lot of heat is generated. That heat can be utilized here for the steam reforming process. So because of that, the external supply of heat for endothermic reactions is brought down. Heat required for reforming is partly provided by the exhaust heat of the fuel cell. So whether it is partly or fully depends upon how much heat is generated in that particular fuel cell. And if that is not adequate enough, you will end up supplying additional heat externally. And as I mentioned earlier, if you consider the efficiency of PAFC alone, where CHP doesn't come into picture, then the efficiency is around 40 to 45%. So now, if you look at the reaction of steam reforming, along with hydrogen, carbon monoxide is also produced. So in the beginning, we realized that if carbon dioxide is present, it is not an issue. However, presence of carbon monoxide is an issue when it comes to phosphoric acid. So why is that? We are using platinum as catalyst, and this carbon monoxide acts as a catalytic poison. So for that reason, we have to handle it carefully. And carbon monoxide poisons platinum catalyst. Reformant gas must be further processed by water gas shift reaction. And as part of the steam reforming process itself, the carbon monoxide that is formed in reaction 1 will react with water, forming carbon dioxide and hydrogen. So as long as it is carbon dioxide, we have no issues, but it should not remain as carbon monoxide. But as this steam reforming process is a multi-step, multi-reaction process, so both reactions will take place. And only thing is we have to make sure that the stream that comes out of the steam reforming before it enters the phosphoric acid fuel cell as fuel should not contain carbon monoxide. And of course, sulfur definitely should not be present. And, if we have a separate pre-processing unit, so desulfurization unit will become part of this pre-processing unit along with steam reforming. So if you recall the reactions, it is only the hydrocarbon that is reacting, and nothing is happening to sulfur if at all if it is present. So if sulfur is present in the starting material, whether it is natural gas or the hydrocarbons, so it is mandatory to subject that to desulfurization. Sulfur should be removed before it enters the fuel cell as fuel. This is about fuel processing in case of PAFC. Of course, this need not be restricted to the PAFC alone. Just because this is the first time we are talking about fuel other than hydrogen, so we are talking about this pre-processing as well. And this might hold good for other fuel cells as well, which operate at a temperature greater than 100 degrees centigrade. So coming to the applications and developments in case of PAFC. By far, this PAFC is the most well developed with respect to technology. And in comparison with other fuel cells, the performance and behavior of PAFCs are well understood. For many years, this PAFC was the only fuel cell that was available commercially. So, for around 30 to 40 years, people were mainly dependent on these PAFCs until the PMFC came into picture. And when it comes to reliability, so it is very reliable. And if you remember, this is one of the disadvantages in case of AFC. So reliability was comparatively less. Even though the current density was high, it was not very reliable. So here the PFC stack is reliable and the quality power is produced by the systems, meaning it is uninterrupted power supply. You can definitely use it for premium applications such as hospitals, banks, where power outage is a major issue, which should not happen. So in such case, definitely you can rely on PAFCs, and it is also known for premium power applications. And capacity may vary from 50 to a certain kilowatts, and 50 to 200 kilowatt capacity plants are very common, and there are examples where the capacity goes as high as 65 megawatt as well. And till date, the largest plant operated is 11 megawatt capacity plant, and it is in Japan. And it is mainly used for grid power generation, so large scale electricity generation, which is an alternative to conventional hydroelectric or power generation by steam. These are some of the applications of PAFCs.